Actually, about a month ago, Dr. Abhinandan Bhattacharjee's talk, part of the ninth lecture in this year's CASILab Saturday lecture series, was interrupted due to some security issues with Google Meet. Although I introduced him last time, I'd like to formally do so again. Today's speaker, Dr. Abhinandan Bhattacharjee, is a postdoctoral fellow at Paderborn University. He's from my home district actually, Halakandi, which makes me especially excited to welcome him. Dr. Bhattacharjee completed his master's in physics from IIT Guwahati and earned his PhD from IIT Kanpur, specializing in quantum optics and optical coherence. His research focuses on spatial coherence, quantum entanglement, and advanced sensing techniques in optical fields, with applications in quantum information, imaging, and ultrafast optics. Today, he will be talking about spatial coherence and entanglement in optical fields. We are honored to have him with us virtually. Please join me in warmly welcoming Dr. Abhinandan Bhattacharjee.
Thank you, Atanuda, for this introduction, and I would like to thank also Shurajit sir for this invitation to present my work. Today, I'll talk about some of my PhD results on spatial coherence and entanglement in optical fields. Those will be basically focused on there are some techniques to manipulate spatial coherence and measure them and focus on why they're important, as well as along the line why there's some technique I'll present for measuring entanglement and some of their manifestations. So that's the outline of this talk. So first I'll start with coherence part. I'll just introduce the basic concept. And before that, just see why coherence is important. Uh, Spatial coherence is pretty important, or controlling coherence is very important in imaging application, and specifically if one needs to do some imaging through complex or turbulent environments. Say, uh, if we have a light source which has very less coherence, it's very good to see things through foggy environment, or imaging through complex media can involve also some biological imaging situation. So in those situations, uh, controlling coherence is very relevant, as well as microscopy. And for long distance communication, just to mitigate the influence of turbulence, uh, control of coherence is also important. So I hope with this we can start why we are looking into coherence. So that's a basic introduction. Suppose this is the light beam we have, and if we focus on the cross section of a beam that you can see, and then spatial coherence quantifies or tells how the correlation at these 2 points x1 and x2 are correlated, or how the fields at x1 and x2 are correlated. And it is quantified through this 2 point correlation function W, which you can see ER. E basically represents the electric field vibrations at this x1 and x2. Now, if I want to quantify coherence in a range between 0 and 1, that's why we normalize it by the intensities at individuals points x1 and x2, and that becomes within 0 and 1. 1 means perfect coherence between these 2 points, 0 means no coherence, and any number in between means partial coherence. Next question is how we can realize it or measure it in a lab or in a realistic situation. For that, one typically use the Young's double slit interferometer and focus on the visibility of this interference fringes that you can see here. And this visibility basically quantifies how the what's the coherence between this point x1 and x2. So next, I'll just give some examples of different type of coherent, different type of sources that can have different types of coherence. Start with a spatially perfectly coherent source. So from the name, you can sort of get an intuition that everything is perfect here. So it's the same double slit interferometer, and here we look at this interferogram as a function of separation between these 2 points x1 and x2, and track this fringe visibility or contrast as a function of the separation. So you can see this visibility is perfect. So that's why visibility is 1 means perfect coherence. We can go to some other separation. Here the fringe period changes, but the visibility is still good. It's perfect, 1. And if we go even further, it's 1. So as you can see, that as a function of separation, the visibility remains always 1. That means a perfect coherence or a perfectly coherent source. Next one is a partially coherent source. So from the name also you can guess, here things will not remain perfect. So we will just track the visibility here as well. So when 2 points are very close, the coherence is very strong, so you can see a very good visibility. Now if you increase the separation, you can see the visibility sort of goes down. That means the coherence between these 2 points x1 and x2 has degraded. Now if you can go further apart, then almost no visibility. There are like very faint interference you can see. So that's why the coherence is almost washed out. So that's what we typically expect for a partially coherent source. As the separation between the 2 point increases, the coherence basically dies out. And this profile has a lot of importance. This profile that you can see in the blue curve, that's called spatial coherence function. So when one looks at a in this different type of sources, people basically measure these profiles, and if this profile is completely like flat on the left side, then we call it perfectly coherent source. If it has this sort of a decaying feature, then we call it partially coherent source. And this width of this profile is sort of we call it the transverse coherence length. And these are the sigmas, the transverse coherence lengths for different sources. For perfectly coherent source is too large. That means any 2 points on the cross section of the beam is perfectly correlated. For partially coherent source, it is finite. And if it's an incoherent source, from the name, it is quite clear that 2 points are not at all correlated. In this case, this sigma c is close to 0. So that's the categorization of coherence. Next, I'll just give an example. What sort of sources you can see? So any sort of modes, like a spatial mode, like if you are using a laser in the lab, the light comes out from the laser. That's a perfectly coherent light source, which typically has this Gaussian distribution. And also, if one can play with the cavity of the laser, then one can produce different spatial modes, which are also representing perfectly coherent sources, like Hermite Gauss modes of different orders. So that's an example of perfectly coherent light field. For partially coherent light field, if I mix these different perfect modes with different weightages in some incoherent manner, then it produces some partially coherent light source. So you can see, yeah, I take these 3 modes and I just mix them with different weightages. This will produce the distribution, final distribution of the beam or the cross section, which will look like this, which you can see much bigger, and that's we call the intensity profile. And within this, so that's the spatial extent or the distribution. And this region, the dark red region, where only 2 points will remain coherent. So that's we call the coherence profile. So hopefully you can get some idea about partial coherence and fully coherent from here. Now I'll just show some math just to tell that the similar representation works for quantum light as well when we talk about photons. So so far, like if I have a classical light source, there we represent everything with the electric field amplitude, that's called E. So that's the electric field amplitude, which has, if we know that, then we can know everything about this light source in the spatial domain, and that's the Fourier transform of that, E of Q. In the quantum case, we represent a single photon state with a state vector rho. And in that case, this E of rho becomes the spatial wave function of that photon. Or one can say that the photon is occupying a spatial mode, which is represented by this E of rho. So that in the classical optics, the representation that we do with this electric field amplitude, in case of single photon case, this similar representation works by the name of wave function or complex amplitude. So that's for this perfectly coherent case. For partially coherent case, we represent it not by the electric field because now there are a mixture of them. So we represent it with this 2-point correlation function, which I introduced earlier. And as for this example, one can think this 2-point correlation function as a mixture of different this Hermite-Gauss modes. And in case of quantum, like this for a classical wave, now if I think about a photon, so one can say a single photon is a mixture of these different spatial modes. And in that case, one cannot represent by a state vector, then one needs to introduce this density matrix representation. So in quantum case, this 2-point correlation function becomes this different elements of the density matrix. So just to show that whether if I work in this with this amplitude or 2-point correlation function, the classical case, or if I go to the single photon case, this measurement can give me all the spatial information of either the field or of the single photon state. So the basics. Next, why spatial coherence is important. Just to motivate that, I'll show you one case. Suppose this is the conventional imaging setup where I want to image an object onto this camera through this lens, and that's how the object looks. Now, if we introduce some scattering or random environment in our setup, which is equivalent to like if I am driving a car and there is a fog and I want to see some object through this fog, then we can see the image becomes pretty bad. We can't see that. So that's how it happens. So here we are using a source called helium-ion laser, which is a perfectly coherent source. And you can see this becomes pretty bad. One of the reasons is that the helium-ion laser has perfect spatial coherence, and when it goes through this scatterer, it basically performs some sort of random interference, and that basically kills the entire image information. And one way to mitigate that or bypass that is to use a source which has less coherence or less spatial coherence, and we'll get rid of this random interference. So that's why one can use a LED. So this is one of the reasons for any normal imaging application like the cell phone that we use or the car light or anywhere, the light source that we typically use for illumination is incoherent. It's one of the important reasons behind it. So you can see with this, at least we can see the object to a better extent than this laser. And we can bypass this random interference effect as well. And it is quite established in the imaging community. The smaller the transverse coherence length of the illuminating light field which is falling on this object, better is the image one can see. That's a very established fact. So now, I'll just do it a little bit more properly. Suppose there's my light source and the object is situated at some distance. Okay. And for a typical light source that we usually use, they have a feature. Their spatial coherence or the transverse coherence length just increases with propagation. So, for example, if you take any light source like an LED, so if you measure the coherence just after this source, it's very low. But if you measure it after a meter, the spatial coherence length increases. There's a feature of this sort of sources. So now, in that situation, if my object sort of moves away from my light source, then I would expect the image quality will fall, right? Because the coherence length will increase, and that causes a degradation in the image quality. And this is a problem because suppose I am driving a car again and I want to see from my car different objects sitting at different distances, and I want to see them with a better quality, each of them. In that situation, what type of source can be helpful? That means I want to see object plane which is separated at different z distances with a better quality. It should not fall like this, or say with equal quality, which means this image quality should remain constant, should not change upon this separation or this distance z. For that, what type of source we require? We need a source whose spatial coherence width should remain constant upon propagation, it should not change. And in our lab, we found a way to generate such a source. And I'm not going into the details of that. I'm just showing one result where we have found a way to engineer a source whose spatial coherence remains same. And here we have tested till 4 meters in the lab. However, it can be like designed or manufactured in a way to this effect should remain over even much longer distances. So now we'll use this source for imaging and compare it with the benchmark source like an LED. So that's our imaging setup where you can see there is a scatterer, and we will use different sources for the imaging. So first we'll start with a helium ion laser, which is perfectly coherent. And we'll look at the images at different z distances. This 10 means 10 centimeter, and this alphas are mean the scattering strength. Higher the alpha is more scattering strength. So you can see worse images as the alpha will increase. So as you can see with laser, it doesn't look too good, but it remains same because the laser remains perfectly coherent upon propagation. So coherence doesn't change, so image quality doesn't change. The conventional source is an LED which we typically use in our daily life. So as you can see here, this image quality is far better than the laser. That's because of very low spatial coherence. Now as we increase the distance, that can affect the, you can see, quality of our image. And that's because the plane, object plane, which is at 50 centimeter, that acts as a illumination which is a higher spatial coherence. Next, I'll go to PIC, which is our propagation invariant coherence source, which we manufacture in the lab or sort of generated in the lab. So you can see at different distances, the image quality almost remains constant, and that's because it has a constant spatial coherence. Now we go to the next alpha, which is the highest scattering strength. This laser can't even image. Conventional source with LED, you can see hardly you can see the first plane. As we go longer distances, this means the object which is sitting at a large distance, we can't see it properly. But still with this PIC source, we can see the object with a good quality. Now, one question may arise in your head that I am doing a cheating because this LED source is a bit diverging type, and as I go further, maybe the intensity of the light is not enough to see the object, and I am just selling it by saying it's more coherent and coherence is doing all the benefit. You might say that it is not bright enough to see that object. For that, we perform a test. So this is the LED. This three images at the bottom is the with the LED source, where we are increasing the brightness of the LED or the power of the LED by 10 times. And as you can see, by increasing 10 times, it is giving some benefit to an extent, but still at this point, the image is not at all good, or not. From this point to this point, the intensity has increased 3 times, but it's not improved. Whereas on the other side, with the PIC source with a much low brightness or much low source power, we can see a much better image. And that sort of clarifies this improving factor here is the spatial coherence, not just the intensity of the source or not the power of the source. We just repeat this experiment for a more realistic situation where in a reflective configuration, here like the light passes through the scatterer, goes to the object and again reflects on the object and again passes back through the scatterer, and then we image it on a camera, which is more relevant for our daily life because we see the object and the light basically goes through the fog or something, reflects back from the object and again passes through the fog, and then we can see it through our eyes, which is basically our imaging system. And here also you can see very similar results and clearly shows the benefit of our propagation invariant coherent source. So at least with this result, I can say that spatial coherence is pretty important for this imaging application. Next, I have established that coherence is important. Next part is how we can measure it, because now it's an important quantity. We should know how much coherence we are dealing with, or what type of how much of spatial coherence is there, or how the profile looks like, and etc. It's a more of a characterization part. And usually one uses this Young's double slit interferometer that I used on my first slide or second slide. That's the usual way of characterizing spatial coherence. However, it is in a practical or in a realistic sense, it's not the best way or best method for characterizing coherence. It has many experimental sort of disadvantages. First of all, one need to use very narrow slits as a result, and also one needs to do a lot of scans, so that requires huge measurement time. With narrow slit, we reduce a lot of flux, so that's why we require more efficient and faster method for measuring spatial coherence. So for this, we come up with a method which sort of schematic of this interferometer looks like this. So here, that's my source that I want to characterize, or the coherence of the source I want to characterize. So this sort of goes through this interferometer. This interferometer, you can see, is more of a Michelson interferometer, except we have a lens on this arm, which is, and this mirror is sitting at the back focal plane of this lens. And there's a purpose behind it that I'll explain in a minute. So now the light field sort of enters this interferometer. In this arm, it basically simply reflects back and goes to this detector or the camera. And that's how the wavefront or the cross section of the light will look like. So that's you consider as your the beam coming from one arm of the interferometer. On the other arm, it goes through this lens and mirror combination and again comes back through the same combination. As a result, the beam that will come back from this arm gets inverted because of this lens and the mirror combination. So that's how it will look. So you can see, as compared to this one, if we come to this one, the y becomes minus y and x becomes minus x. So at the camera plane, every x will interfere with minus x and every y will interfere with minus y. And that allows me to basically get the correlation between every x and minus x point, every y and minus y point. And from that, we can, by just recording these images, we can basically retrieve the coherence information. So that's how the image on the camera will look like. That's an experimental image. When there is a zero phase difference between these two arms, and when there is a pi phase difference between the two arms of the interferometer, if we just subtract it just gives us a coherence function, which is this. And this is quite beneficial because by just collecting two images, we are able to reconstruct the entire coherence between rho and minus rho. Rho basically two-dimensional one. Rho means xy and minus rho means minus x minus y. We are able to get this coherence function, as well as you can see in the individual images, there are some noisy background. By the subtraction, we are able to even get rid of that background as well. So, which is quite, in one sense, it's a bit of a background insensitive method. So now we will use this method to characterize this source. So now what we do, we basically use some LEDs at this plane, and there's another lens. So but if I install this LED at the backfocal plane of this lens, and then we'll look at the spatial coherence of the light field after this lens. So for this combination, we expect the coherence function looks something like this. This pattern, this is the coherence function that we are expecting, which is basically Fourier transform of this LED pattern, and that's what we are able to measure. So you can see with a very good quality, we are able to perform these measurements. I just repeat it for another settings where we, in the primary source, we place this 9 LED, and that's what like theoretical coherence function we expect, and that's what we measure. And this can be done with a very good quality. So that shows that by doing this very simple interferometric design, we are able to measure such complicated coherence functions with a very good.
Abhinandan, I think
yes,
Shurajit sir wants to ask something.
yes, sure, sir.
Yeah. So Abhinandan, I want to ask one simple question. That is, source what you are using is a ordinary in primary that is there is the coherent source, right? That is in
Yeah, no, this is this just an LED. 9 LED bulbs are sitting at the
okay.
back focal plane of this lens.
Okay, okay. One point I want to ask. Suppose
Yes.
these days, that is today, we have many single photon source. Okay.
Yes, yes, yes.
So if you perform this type of same experiment using this single photon source, will you
Yeah.
think that there will be a difference in the outcome?
Oh,
What
no, no, no.
results?
No, this method will perfectly work for single photon sources, and I will show one of the results that we also apply for the single photons that come out from a uh, source which is called SPDC in
Okay.
later slides.
Okay.
This method is insensitive with the fact that whether the my source is a single photon source or a classical source.
Oh, okay, okay. Okay.
So
Okay.
if I can add one more point, so for example, this is a normal LED that we use in our different purposes. So if I put a sort of an attenuator that can kill the power of the LED, okay, or the brightness of the source, and one can put many of them together and reach to a level where you can see, or we can see, the light field is very much at the level of single photons. Okay, the higher photon number components are very less, or at the level of single photon. In that case also, this will perfectly work. Is it fine? Hello.
Yeah, yeah, yeah. It's okay.
Okay.
It's okay.
Okay.
Please continue.
Okay. Thank you. So that's the coherence part. So I present one application of spatial coherence and then one characterization scheme. Now I'll quickly move to spatial entanglement, which is also a very similar concept, but it's more of a quantum. So why spatial entanglement? It started like many years ago, but in recent times, people have found as a motivation, like it is very good to do some sort of coincidence-based imaging, where the coincidence-based imaging has its own advantages. Say, it's very insensitive to noise, which is somewhere here. You can see that if you do a classical imaging, you can see there is a lot of background involved. Here you can see with this quantum imaging, not so much of background, as well as you can do better noise insensitive measurements, and sometimes one can start with two light beams which are sharing some sort of a strange correlation, and you put object or introduce the object in one in path of one beam, and you can see the image that is coming out on the from by measuring the other beam. So this sort of exciting applications are around. So that's why that makes this area of studying spatial entanglement or correlations between photons very interesting. So now, before going into the spatial entanglement, I'll just quickly go through this uncertainty principle that we usually have seen, known by Heisenberg uncertainty principle. So the uncertainty principle says if I have a wave function which can be described by this plane wave, that means it has a single direction, or in quantum language, it's a single momentum vector. In that case, the spread in the momentum is zero, but if I look at it in the space, it is infinitely big. So that means the spread in position is pretty large. So that tells that for a given state, I choose just plane wave. For this state, if my uncertainty in position is very large, sorry, uncertainty in momentum is very small, then position is pretty large. That's a feature of a state. It's nothing to do with the measurement, it's more the feature of the state, which is described by this plane wave. Next, if I take a point source, so a plane wave before going to point source, a plane wave one can realize in a lab. Suppose if I can get a collimated beam and try to make that collimated beam to a single photon level, then one can say, okay, it's very close to a plane wave function, where since it is collimated, so it's a unidirectional more or less. So that means the p vector spread is very less, and since it is collimated, it should be infinite extent. So that's why spread in position is very high. If I have a point source, if I take any point source, it basically the spread in the position is very less, but can take a very small LED light source, and you can see it spreads all over the room. That says it has many spatial frequency vectors, or in quantum language, it has many momentum vectors. So whenever, if we have a wave function or the state of an object that has a very narrow distribution in position, it has a very large distribution in momentum. And that is sort of captured by this Heisenberg uncertainty principle that says for a given wave function, we cannot find the delta x and delta t. Delta p is minimum value can be h bar by 2, otherwise it's more than that. So that's how this. And one key point here is that all of this thing is true for a single photon system or a single particle system that we typically read in quantum mechanics. Now I'll go to a two particle system, and I'll just introduce through a realistic setup. So there is a nonlinear crystal. Don't worry about it. And we are throwing some high intensity laser light, which is a UV laser beam on this crystal, which we are calling as a pump. And now what will happen? This pump beam will interact with this nonlinear medium, and one of the pump photon, you can consider the pump is like a bunch of many photons or millions of photons coming together. And one of the pump photon gets converted into two higher wavelength photons, or that's why I put them red, which I am calling a signal and idler. Okay, so now, sorry, I think due to some reason, I don't know, this image is missing. Sorry for that. So this process basically follows the energy and momentum conservation. So whatever the energy of the pump, that should be sum of the energy of the idler and signal. So that basically says if the pump is coming with some frequency omega p, the frequency of the signal plus the frequency of the idler, sum of them should be equal to the omega p, and that's the momentum conservation. Okay. Now, how it is related to the previous slide, that position momentum, now I'll come to that. Now, if you make a measurement on the idler slide, sorry, before going to that, just want to clarify that. If you look at an idler or signal, if I look at a transverse plane, it has this big distribution, okay? Now, if I come with a detector or a pixelated detector and see the signal comes at this location for a given measurement, the signal photon hits 1 pixel of the detector, and conditioned on that, if I just look at the what is the distributions of the on the other side or of its partner, for that we need to take many measurements on the signal side. Then we see the distribution of the signal will be very narrow, and the uncertainty of that distribution, we call it the conditional uncertainty. And similarly, if we do it for the momentum, if we find a way to detect the momentum of the idler and conditioned on that, if we look at the signal, we'll get another momentum uncertainty. And if we take the product of these two uncertainties, and if we see that it is less than 0.5 h bar, then that's the signature of spatial entanglement. Or some people say that's the signature of EPR type entanglement. And that basically tells this conditional uncertainties, which if I look at the uncertainty only on the of the signal or the idler, then they will be greater than 0.5 h bar or h bar by 2. But if we look at in this conditional manner, then I can simultaneously measure or get this uncertainty in position and momentum less than 0.5 h bar, and whenever one sees that or observes that, that's the signature of position momentum entanglement. And this exists between this conjugate basis. There is another conjugate basis, another basis we can take, that's sort of angle. So if I make a detector where the idler is only detected in this angular region, and conditioned on that, if I look at the angular distribution of the signal, I can get this uncertainty in the signal. And similarly, its conjugate variable is orbital angular momentum, and one can do one can make detection system which can measure in the orbital angular momentum domain or basis. And if one make a detector which can only detect on the idler side, suppose some Li, which is a fixed orbital angular moment of the idler, given that one will see a very narrow spread on the orbital angular momentum of the signal. And this also follows or sort of violates the uncertainty principle. And in that case, we call it angle OM entanglement. So these are the different types of entanglement one can experience in the spatial domain. There is another way of looking into it. So as I have mentioned, if you look at signal part and idler part individually, they are like, one can think it as these are the mixture of different these spatial modes. Okay. Now, same for this part as well. Now, if I have a way to detect only this spatial mode on one side, and if I detect this particular spatial mode for this part, and conditioned on that, I look at what's the spatial mode on this side, then I'll only see this spatial mode for the other side. So if I would like to join state for both of them, in that case, I would say if signal is in this Gaussian mode, idler should be in this. Similarly, if I make another measurement or another way of detecting spatial mode, and if I see on the signal side, if I have this sort of spatial mode, conditioned on that, if I look at on the idler side, I will see idler has this particular spatial mode. So you can see if the signal is this one, idler is this one. And similarly, we can for the higher order like this. And if I can represent a joint state of signal or idler in this particular manner, that's also a way of representing spatial entanglement. Here, the catch is that you cannot represent the state of the signal as a, like, I cannot represent the state of the signal time state of the idler as their joint state, right? Because here you can see these are like represented in a sum. So that's another way of representing entanglement. So that's a basic definition or introduction to spatial entanglement. Next, I'll just show what is the technique that we developed for measuring it. Typically for measuring, and I will talk mostly about entanglement for pure states. So for measuring entanglement or characterizing entanglement, one needs to do a joint measurement on the both the parties, signal and on the idler. Okay. And by doing that or doing joint measurement on both of them practically is difficult, I would say, with the given detection and the methods that are available. And as a result, if I want to verify entanglement through those uncertainty products, we found that, or in the literature, those measurements are not very accurate. They are like off by 66% or 43%, even with this very high impact journals that people publish. There are also the measurements are not very perfect. That means those uncertainties that people are using for characterizing entanglement, they are not able to measure it in a given setup with a very accurate manner, which is not very helpful, because those uncertainties one needs to know very accurately to use this entanglement for any application. So here we found a way where we are interested in finding these uncertainties, which I'll again recap. It's like, if I detect idler on one side, I would like to see what's the uncertainty of the signal on the other side. And for doing that, we found that we don't need to do a joint measurement. We can just measure the signal photon on one side and get this conditional uncertainty, which typically obtained through a joint measurement. So we found for this uncertainty, we require this conditional probability distribution. And for the given situations, we found that this conditional probability distribution basically maps to the coherence function of the spatial coherence function of the signal photon. And because this signal is a mixture of these different modes, and which makes it incoherent mixture of different spatial modes, which I talked earlier, that makes them partially coherent. And that coherence function or coherence profile is same as this conditional distribution profile. So if I can measure only the coherence profile of the signal, then that gives me the information of the conditional uncertainty. And similarly, if you can do it in the momentum, that will give me the momentum uncertainty. So that gives a way to characterize entanglement. Instead of detecting both of them together, just measure the coherence of one of the parties, and that gives the information of this conditional uncertainties. So I have already shown one method for measuring spatial coherence. So we implement this particular interferometer on the signal part that we generate in the lab. The signal beam goes through the interferometer, and that's the result that we get. So this solid line you can see, that's the expected conditional distribution for our source. And by using that interferometry, that's the dotted the dots that we get, and you can see this dots are on top of those solid curve. That shows a very good match between theory and experiment. And similarly, we do it in the momentum domain. For to perform any measurement in the momentum domain, what we need to do, we just need to do a Fourier transformation. So we just basically put a lens and go to the backfocal plane of the lens. That's the Fourier plane. And any momentum measurement in optics, people usually do by placing the detector at the Fourier plane. And that's the uncertainty product you can see, and it's less than 0.5 h-bar. So that's, we are able to verify entanglement just by doing an intensity measurement. And earlier, the accuracy you have seen, or the mismatch you have seen, like 60% or 43%. Here, with this measurement, without doing joint detection, just by measuring the coherence profile of one beam, the mismatch sort of comes down to 14%, which is very important from an experimental perspective. And when the result was published as the most accurate measurement that was in the literature. So with this, I'll move on to the next thing. So that's the measurement of entanglement that we have. Next, I will talk about another effect that we have seen, that's on the propagation. So before going to the propagation of spatial entanglement, I just want to highlight that. So to use entanglement for any realistic application, it is very important to verify the entanglement remains in realistic situation, like over long distance propagation, as well as in turbulent environment. Because if you want to communicate or do some long distance imaging, and if I use entanglement as my resource, then that entanglement should remain there, or one should be able to measure entanglement as for long distances. And you can see these are the different examples where the propagation of entanglement has been explored in polarization for time bends, but not much in the position momentum or for angle OM. So our focus will be on that. So here also we'll again talk about entanglement in terms of those uncertainties, conditional uncertainties. And we found that if I have this PDC system or parametric down conversion, which I saw earlier, for this particular system, the conditional position uncertainty, it sort of changes in this manner upon propagation. That's for the PDC. And for angle, it's very interesting. Initially, it increases like the position uncertainty, and beyond a certain point, it sort of decreases. And that sort of gives a hint that if we sort of characterize our entanglement through the product of this uncertainty, maybe angle OM uncertainty can give a better signature over long distance propagation as compared to position momentum. Although for to talk about entanglement, we also need to look at the conjugate partner, like for the position, we need to look at the momentum, and for angle, we need to look at the orbital angular momentum. So for a parametric down conversion process, since in this process energy and momentum remains conserved, as a result, these uncertainties are not I would say this uncertainties are independent of the propagation distances. So if we track the uncertainty product for position momentum, it will follow this blue curve, and for angle OM, it will follow this red curve. So that means the angle OM product beyond a certain distance will just decrease upon propagation, which is quite interesting, and it was not explored earlier. So we perform our measurements. So as you can see, that's for position momentum. So if it is less than 0.5, you can see entanglement. So this yellow region where one can see entanglement. So with our experimental data, if we qualify or if we characterize entanglement through this product, you can see one can only see position momentum entanglement from this source just after few centimeters from the propagation distance. And after that, one cannot verify it through this sort of measurement. Whereas in angle OM, you can see that like position momentum, initially if we have some entanglement, then we can't observe any entanglement. And after 24 centimeter, we can again start seeing the entanglement, which is a very new signature, I would say, in this basis. And next thing we verified, it's very important to verify anything in the presence of turbulence, because in a realistic applications, turbulence or scattering are very common. So we verify this entanglement signature in the presence of turbulence. So even in the presence of turbulence, we only verified what happens to angle OM beyond after long distance propagation. So you can see, so that's the profile that we get in the presence of turbulence. So this entanglement sort of revives and it comes back even in the presence of turbulence. And just compared it without turbulence, we plot this trace. So if I compare the entanglement when the turbulence is not there and when the turbulence is there, so you can see this green profile just shifted. So if I want to use this OM entanglement as a resource in case of turbulence, in the presence of turbulence, this angular entanglement is not completely lost. It's just that we need to propagate more to get it back. So that's a cool feature we have seen in the case of angular entanglement. So with this, I would like to summarize my talk. So in the first half, I talked about measurement of coherence and applications of imaging application of coherence. In the second half, I was talking about one way of measuring or characterizing spatial entanglement through intensity measurements or count measurements on only one of the partner, like the signal or the idler. And then we have shown some entanglement revival signature even in the turbulence in case of angle OM, degree of freedom. And I would like to thank for my work, my PhD supervisor, and all my collaborator. I would like to thank you for your attention. And with this, I'd like to end my talk. Thank you. And I'm open for any question as well.
Abhinandan.
Yes.
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 For some network issue, I cannot open my video. So just can you hear me?
Yes, yes, I can hear you.
Okay,
Yes,
okay.
yes, I can hear
Now,
you.
okay. So I have two questions. You can go back to the slides where you showed the tree diagram about spatial coherence and spatial entanglement.
Uh, which one? Like this
The tree diagram.
tree diagram.
The, where you
Sorry.
wrote about the spatial
You mean the outline?
outline.
Okay.
Yes, yes. Now, what I've understood from your talk is that you are actually, I mean,
I'm sorry, your voice is breaking. Means I can't hear you properly.
okay. Can you hear me? I mean, I think, can you hear? Hello?
Yeah, your voice was breaking.
Yeah.
Uh,
Now can you hear me?
yeah, it's audible, but yeah, breaking or sometimes it's lagging.
Uh, am I clear now?
Yeah, it's better now. Can you please tell your
Okay.
question?
What I'm saying is that I think you are an experimentalist. You do experimental works, isn't it?
Yeah, yeah, yeah. I'm an experimentalist.
Okay. So what you have said about your research works is good. Okay, but can you tell me? I mean, I didn't understand the part where you talked about spatial coherence and measuring spatial coherence and spatial entanglement. What sort of measure you use actually?
Oh, okay. So, yeah, sorry, I was a bit quick over there. I can maybe explain it again. So, my goal is to basically find this conditional uncertainties. Okay, this product. This is called EPR product, or people call it EPR type correlation. If one can find this product, am I audible?
Yes, 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 yes.
Okay, so my goal is to find this product, and for finding this product in experiments, what I didn't show any setup because it's too complicated sometimes to show. So I didn't show any setup in experiment. What we do, we put a detector on this idler side, okay, and on the idler side we put a detector with a single pixel, and we get some count, and simultaneously we look at the counts on the signal side, and that's how we can measure this we have a multi-pixel detector on the signal side, and that's how we basically get this p of yes yi, or p of this conditional distributions, and which are quite difficult, or that has different issues in a realistic experiment to measure them in that manner. So what we have found, instead of doing this joint measurement, we found that we need to find somehow this conditional probability distribution, p of yes yi and p of this p of sy p of iy. So we found that for this parametric down conversion process, which is a very common way of rating spatial entangled uh, light field or spatial entangled spatially entangled photons. For them, we found that. Let me go to the slide. Okay. So we found that one do not need to measure this in a joint manner. This particular probability distribution is similar to this W, which represents a spatial coherence function of the signal beam or the signal photons. So if I measure the spatial coherence function of the signal photon, then it basically maps the conditional probability distribution. And if I know the conditional probability distribution, the width or the variance of that distribution is my uncertainty. So I just measured this coherence functions in the position and momentum domain for degree of freedom, and from that I extract those conditional uncertainties. So these are you can say these are basically just different experimental conditional distributions that we measure using this interferometric technique. So for measuring coherence function, I use my interferometer that I proposed or have demonstrated earlier. And by using this interferometer, we get these traces, and then we look at the uncertainty of these distributions, and the product will give me the EPR type entanglement. Is it clear, or shall I
Yeah,
explain?
yeah, yes. It is clear, but the slide you are in now, just now, the
Yeah,
slide you are showing, the
yeah.
curve that is there in the below, is this curve a normal curve?
Normal curve means Gaussian
Norm,
distribution, you mean?
Gaussian distribution, yes.
Yeah, yeah,
So it is a normal curve, and it is a standard normal Gaussian distribution, isn't it? The mean is zero.
yeah, 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 yeah,
And in the left hand side diagram, you have taken from minus 60 to plus 60, and in the right hand side diagram is minus 17 to plus 17.
yeah.
What is the difference between the LHS and RHS diagram? Why are the two limits have been taken?
Oh, okay. So this one is for position. This is for measuring the position distribution, and this is for measuring the momentum distribution. So that's why you can see the units are also very different.
Oh, okay. So if I increase the right hand side limit from say from minus 60 to plus 60, then what will happen?
Oh, so you can see this red curve. So the red dots or the blue curves, you can see they are representing probability distribution, and there is no probability even after minus the probability distribution only has some significant value